This lecture is about sedimentary rocks. Up until this point of the semester, we have been focusing on igneous rocks, or those that are produced through the melting of pre-existing rock to form magma or lava, which then solidifies to make igneous rock. But igneous rock is one of only 3 major rock types in the earth. And these are all related to one another through something called the rock cycle. And today we're going to talk about sedimentary rocks. And sedimentary rocks are made by the erosion, transportation, and redeposition of little bits of pre-existing rock. So you can get to sedimentary rocks through the rock cycle from either weathering and eroding igneous rocks, like so, or you can weather and erode metamorphic rocks, like so, or you can even start with a previously existing sedimentary rock, weather and erode it, and return to a new type of sedimentary rock. When we get together on Thursday, I'm going to show you a video on the rock cycle that might help to link these 3 types of fundamental rocks, or these 3 fundamental rock types to one another. So sedimentary rocks are really cool because they form like layers, and those layers are like the pages of a book. They record a history of ancient events and ancient environments on the ever-changing face of planet Earth. This is text from your textbook, which is kind of overly dramatic and funny. Like a book, this history can be read like by geologists, but it is true. So sedimentary rocks form in layers, and hopefully you can see in this aerial photograph of the Grand Canyon all of the many layers that make up the Grand Canyon. And so we can study this top white layer, or this white layer here, or these red layers in here, and we can learn about what the surface of our planet was like at the time that those layers were deposited. So we can read back through time, through these layers, and kind of peel away the pages of Earth's history. Here's another view from the Grand Canyon, this time in Western Grand Canyon in the Inner Gorge. And this is a great photograph because it allows you to see that sedimentary rocks are layered rocks that form at the surface of the Earth, and so therefore are usually on top of other deep forming rocks. So in this case, we could sketch on top of this photo and create a geology rendition of the photo in which you can see the pre-existing basement rocks at the bottom of the gorge that are capped with these cover rocks that have this really distinctive bedding. The boundary between the basement and the cover rocks is this thick black line here, which we would call a contact. And so everything above the contact is sedimentary rock, and everything below it, in this case, and in this picture, is igneous rock. Okay, so if we're going to talk about sedimentary rocks, we have to know what sediment is and where it comes from. Sedimentary rocks always form at Earth's surface through cementation of weathered fragments of pre-existing rocks, or fragments of shells, or the accumulation of organic matter, or the precipitation of minerals that are dissolved in water. Sediment refers to loose fragments of rocks or minerals that are broken off of bedrock. It can also refer to minerals that precipitate directly out of water or shells and shell fragments. Okay, so sediment you can think of as being the loose debris that develops at the surface of the Earth as a result of weathering. So it makes sense to, if we're going to talk about sediment, to talk about weathering next. But before we do that, I want to point out this really cool photo here that's on the left, because it gives you a hint at why sedimentary rocks are so cool. In the top, we've got a picture of a beach, so you can see the ocean out here. And what you can see is ripples that are developing in the beach sand. I'll just outline a couple of the kind of ridges that mark the tops of some of these ripples. So you can see these ripples very clearly developing in the sand. We live next to the ocean, and my guess is that most of you have walked on beaches, and if you've ever been to a tidal flat or a place where the water is a little calmer, you've probably seen the development of ripples like what is shown in this picture here. On the bottom is a sedimentary rock. So this rock is, I think in this case, 150 million years old or so. And what you can see is that this rock preserves those same ripple features. And so sedimentary rocks are really cool in that they capture in the geologic record processes that are observable to us at the surface today. Okay, weathering. Weathering occurs when loose fragments of rocks or minerals are broken off of bedrock. Okay, so in this picture, we're looking at fresh or unweathered granite down below. So this stuff down here is unweathered granite, and this stuff up here is weathered granite. So it's being eaten away at by the wind and the rain and freeze-thaw cycles and that sort of thing. And so what was a big cohesive chunk of granite is being broken down into smaller pieces of granite and or individual mineral grains that formed in the granite. And that's significant because once you break a big, solid, coherent chunk of rock down into little pieces, it can then be moved around the surface of our planet by wind and water and ice, and can be redeposited to form a new sedimentary rock. So again, we're looking at pictures on the top of weathered granite. This is probably from Joshua Tree. And on the bottom is a picture of sediment. And you can hardly tell the difference between the two pictures, but in the bottom, you can imagine walking along a path, say through Joshua Tree, and your feet crunching over the gravel. And the gravel would be essentially tiny little bits of the weathered granite that eventually, because a rainstorm or a big gust of wind blew some of these weathered pieces off and they landed on the ground, to form this kind of mat of loose rock and mineral debris. That's the sediment. And that sediment is going to be moved around the surface by wind and water primarily until it finally reaches a low spot where it can become buried and consolidated and turned into a sedimentary rock. We'll talk about that in a moment. Weathering can be physical, so it can occur through joints that develop in large masses of rock. Once you have those joints, it's very easy to kind of bust apart rocks using tree roots or by getting water in there and having the water freeze and expand. But these are examples of physical breaking apart of rock. Here's a perfect example of rock that is in the process of being physically weathered. This is a big slab of sandstone that has big joints that are forming in it, and those joints are becoming enlarged over time, mainly through water that runs through it. I suppose rock climbers like myself and my friend Scott are aiding in the development of weathering and erosion in those joints, but it's a good example of physical weathering. You can have wedging. So once you have those joints developing, you can wedge the rocks apart. And that can happen commonly through root wedging. So tree roots can grow on the surface of the rocks. And of course, the tree roots are going to take advantage of cracks and joints because they want to get down to nutrients and water beneath the surface. And when they do that, of course, they kind of bust up or wedge apart the rocks. Frost wedging, so again, water getting into the joints and then freezing and expanding and breaking apart the rocks is another way. You can also have salts. So imagine now that that water is carrying a lot of dissolved material in it, and then when it precipitates, that material can precipitate out of the water in the form of salts, and those salts can kind of wedge apart the pre-existing rock. So all of these processes that I'm talking about now, these physical weathering processes, can take solid rock and break it up into little pieces. Chemistry can do that as well. So imagine that you have rock that's running over, water that's running over your rock. In this case, in the picture on the right, we've got this bumpy gray limestone. Limestone is made of the mineral calcite, CaCO3. And when you add water to that, if the water is slightly acidic, if it has a little bit of HCl in it, you can actually produce a new salt and drive off carbon dioxide. And in the process, what you do is you are essentially breaking apart this CaCO3. So in the picture that's shown, it's actually a simpler process that's shown, but the water molecules are acting to essentially pluck away ions. So in this case, you've got sodium chloride, so halite mineral, which water is breaking down. And you guys know this already, that salt is soluble in water. So if you put enough water across certain minerals in the Earth's crust, it will start to dissolve. Those minerals and rocks can be partially or completely soluble. Physical and chemical weathering go hand in hand. This should come as no surprise. As physical weathering works to break down rocks and minerals into smaller and smaller bits, you're exposing more surface area of those bits, which can be then targeted more efficiently by water, which does the chemical weathering part. So as your rock breaks apart due to physical weathering, the surface area increases and therefore more chemical weathering occurs. Okay, so we've really been focusing on this part of making sedimentary rocks, the weathering, because that's step one. First, you've got to take a pre-existing rock and you've got to break it into little pieces. This is where, in the weathering step, is where you make sediment. Okay, so most sediment gets made that way. You can also have sediment being made through this chemical dissolution, where the pre-existing rock is now being partially dissolved, and so some of the elements that were in the rock are now existing as ions in a solution. Both of those count as weathering. Okay, but let's focus on the physical part of it. Once you've made sediment, you then have to go through several steps in the several processes in order to turn that sediment into sedimentary rock. The first thing you have to do is erode it, meaning you've got to move it away from its source. Okay, so weathering and erosion tend to go hand in hand. Part of moving it away from its source involves transportation. Transportation is usually, in most cases, accommodated by rivers, but it can also be, sediment can also be transported by wind or by ice through the movement of glaciers. And in all cases, well, not in the case of wind can do funny things, but I should say in most cases, in the case of rivers and glaciers, sediment is being moved from high elevation places to low elevation places, right? Because water and ice are always going to work at the mercy of gravity. So generally speaking, when we make sedimentary rocks, we're going from the mountains to the oceans, or from high elevations to low elevations. So the high elevations are where the mountains are, where all the rocks are exposed and being weathered, and then they're being transported down slope. Eventually they're going to reach some place where the transportation stops and the sediment gets deposited or left behind. You can see deposition happening actively on beaches and, of course, in the deep oceans if you were to go and crawl around on the floor of the deep oceans. So I've got a little cheat sheet. We can look at this slide. But now it has these different processes described for you. So this is what has to happen to make sedimentary rock. And it has to, of course, start with the disintegration of pre-existing rock, and it has to end with deposition. But actually, we don't end there, because once the rock is deposited, or once the sediment is deposited, we still have to turn it into rock. And we're going to do that in the case of clastic sedimentary rocks, clastic sedimentary rocks. So I'm showing you here the four main classes of sedimentary rocks. Probably the most easy to understand and the most abundant on planet Earth, so therefore you could argue the most important, are these clastic sedimentary rocks. A clast is simply a bit or a chunk, to use technical terms, of pre-existing rock. But it can also be a shell fragment or something like that. Okay, so a bit of pre-existing rock or shell. And so a clastic sedimentary rock is one that forms through clasts that are eroded, transported, deposited, and lithified, just like I described, until you're left with a brand new rock that is just a cemented accumulation of sediments through something called lithification. And I will go back to that previous slide in a moment. Once the sediment is deposited, it has to undergo lithification. Lithification literally means turning into rock. Okay? And so as sediment gets deposited and more sediment gets deposited or laid down on top of it, the stuff that's on the bottom undergoes increasing pressure. The pressure tends to compact the sediment and to drive away water and to lead to the production of cements that will bind the little bits of sediment together to make sedimentary rock. And that's what's shown in this little 3-part time series figure. So this is the process by which you make something called. The types of clastic sedimentary rock that can form depend primarily on how big the clasts are. Those can range from boulders all the way to really, really tiny mud-sized fragments. It depends on the composition of the clasts. So are the clast rocks or individual mineral grains? And if they're minerals, are they mostly quartz, or are they quartz and feldspar and biotite? Are they, what are the composition of the clasts? How rounded they are. So if they're really angular, that tells you something different than a clastic sedimentary rock that's made of super rounded spherical grains. There's this issue of sorting. Sorting refers to the variety of different grain sizes that exist in the rock. And lastly, we can classify clastic sedimentary rocks based on the type of cement that binds them, although that's much less important. And typically that cement is either a quartz-rich cement or a calcite cement. Okay, so let's talk about size. Clasts or pieces of sedimentary debris can be very large. They can be the size of big boulders, or maybe cobbles, like grapefruit-sized things. They can be a little bit smaller, like pebbles, or even smaller than that, like a pea. But all of these things, from like pea to boulder size, are all pretty coarse, and so we would lump them into one size category that we would call gravel. Once you go a little bit finer than gravel, you get into sand, and we can subdivide sand into coarse, medium, and fine. And I'm sure you guys have all walked on a beach and know what sand feels like. If you go a little bit smaller than fine sand, you get into something called silt. Now, silt is somewhere between a really kind of fine powder and a really fine-grained sand. So you'll still feel, if you were to rub silt together in between your fingers, you would still feel a little bit of that abrasiveness of sand, but it would be coarser, but it would not be as fine as, say, like a powder. Clay is is a clastic grain size that is really, really fine, so it would be in that kind of powdery size fragment. Roundness, just what it sounds like. Clasts can be angular, like on the left, or they can be super rounded. So you can see that these grains down here appear more spherical, and over here on the left, I'll outline a couple. They're really angular and kind of chunky looking. Okay, and so roundness is important because the more rounded the grains, the greater the degree of transportation. Okay, the same is true with size. The smaller the grains, the greater the degree of transportation, because the heavy stuff, the really, really large clasts are heavy. They're not going to get transported very far before they're deposited. Okay, sorting. Sorting is a measure of the uniformity of grain sizes. So something that is very, very poorly sorted has grains that are really large, but also grains that are teeny tiny. Something that is very well sorted has grains that are all the same size. So a clastic sedimentary rock that is very well sorted indicates a rock that has been very far traveled, because the traveling through glaciers and mainly rivers filters the grains for grain size, such that only, the fine sand makes it to the shelf of the ocean and only the clay-sized particles makes it to the deep ocean, etc. Okay, and lastly, I'll just mention again that quartz and calcite are the most common cements, and these are the material that binds all the clasts together when they're being compacted and lithified to turn into clastic sedimentary rock. So these different kinds of clasts, what they're made of, how far traveled they are, they make different types of rocks. So think of the kind of rock that would form from angular blocks of rock deposited right next to a steep mountain front on a talus slope. So imagine that you're like one of these guys here that's walking around. You can see that they're in the mountains. Here's a really steep slope here. So they're high in the mountains, and this is chunks of the rock that's probably just rolling down this hill slope from right above them. If this material gets turned into a rock, gets lithified somehow, it makes a kind of rock that we call breccia. So breccia consists of really coarse-grained, poorly sorted clastic material that would not have been traveled very far, and so therefore would be deposited close to the mountain front. If we go a little bit farther away from the immediate slope of the mountain front, we still have really, really coarse material. It's not very well sorted, but the clasts themselves are better rounded. So you can see here they're not as kind of jaggedy and angular. We would call this type of rock a conglomerate, but it also suggests to us that this clastic sedimentary rock has not traveled far from its source. Here's a picture of conglomerate in the wild, so to speak. So all of these are clasts that are gravel sized. In most cases, I would call these cobbles. But you can see that they're not super angular, so we would call this a conglomerate and not a breccia. Let's keep moving away from the mountain. So the talus slope that might make the breccia, maybe you'd find that, up here. And the conglomerate might be forming in like a river that's coming out of the mountain. But what if you get down into the apron here at the foot of the mountain as you enter the valley? We call that wedge-shaped accumulation of sedimentary material an alluvial fan. Alluvial fans are going to have finer grain material. So now we're not talking about gravel, but we're talking about sand. Although that sand is probably going to be coarse-grained, angular, not very well sorted, and that's in fact what you're seeing here in this picture is a real immature, we would call it, sandstone, because it hasn't gained maturity. It hasn't hung out in that sedimentary system for a long time, being transported downslope. The farther you go in that alluvial fan, the finer grained, better sorted your sandstones are going to be. And now let's pretend that we've gone from the alluvial fan, where we made, in this case, a really coarse sandstone, and we're going to come out into the valley floor. And this sandstone from the previous slide looked very different. And so now we're in the kind of lowlands away from the mountains, but we're not all the way out to the oceans yet. Now we're making sandstones that are maybe well sorted and that have, say, medium size grains, and those grains are reasonably well rounded. We would call this another kind of sandstone, but you can see that this one clearly tells you that the grains have been worked more in the sedimentary environment or in the surface environment. Sandstones can preserve all sorts of features like cross-bedding, which is seen here. And I hope to touch on that in the next lecture that I do for you guys. Here's another picture of a famous sandstone from Monument Valley, Arizona. And if we go even farther away from our source, then we're going to get a sedimentary rock that forms from sediment that's even finer grained. So we've touched on gravel. Gravel, when solidified, can make breccia or conglomerate. Sand can make sandstone. Silt can make siltstone. I don't have a slide for that in here. And if you get down to the clay size, so the really fine-grained stuff, of course, is clay. You can think of clay as also being analogous to mud, which is very fine-grained. Mud is just not a technical term. That solidifies to make the sedimentary rock shale. Okay, so gravel is to breccian conglomerate as sand is to sandstone and clay is to shale. And typically when you're making shale sedimentary rock, you're pretty far away from your original weathered source. Okay, I'm going to leave it there. Tune in for my next lecture on depositional environments.